Our Strachey Lecturer today is Subbarao Kampambati. He is a professor of computer science at Arizona State University, and he studies fundamental problems in planning and decision making, and is motivated particularly by the challenges of human-aware AI systems. He holds a number of prestigious fellowships, including a fellowship from the Association for the Advancement of Artificial Intelligence, AAAI, the American Association for the Advancement of Science, the Association for Computing Machinery, and he was a NSF Young Investigator. He served as president of AAAI, the Association for Advancement of AI, and has served as a trustee of the International Joint Conference on AI, and has been a founding board member of the Partnership for AI. His views on research, as well as progress and societal impact on AI, are featured in many multiple international media outlets. And in particular, he writes a regular column on artificial intelligence for The Hill, which is both very entertaining and extremely informative. And I recommend it if you're interested in learning more about the reality of AI today and in seeing some commentary on AI developments. He's also on Twitter and is an extremely entertaining person to follow on Twitter, making lots of interesting remarks about current developments in AI. So, Rao, it's our very great pleasure to welcome you. I'm sorry we can't welcome you face to face, but as I just said to you offline, we hope that we will be able to do so at some point in the future, and you would be most welcome. So, Rao, over to you. Thank you.
Thank you. So I'm assuming you guys can see my screen. Okay. So thank you all for coming for this lecture from wherever you are, and thanks Mike and Oxford CS department for inviting me to give this lecture. So I am going to be talking to you today about how to get AI agents to interact and collaborate with us on our terms. So let me get started by thinking about how we basically see AI being shown or being represented in popular culture. Typically, AI systems are already from the beginning, from the get-go, are seen as things that are like companions to humans, whether you start from like 2001 Space Odyssey, Hal, hanging around with Dave, Samantha hanging around in Her, and also, of course, Ava in Ex Machina. Even obviously the popular culture, the novels, Ian McEwan and most recently Kazuo Ishiguro are talking about robots that work. The way they imagine, the way we imagine AI agents is they will be working with us. They'll be sort of companions, and you will almost treat them almost as if they're humans in some level. So this is AI in popular culture. So you would think that instead of the gloom and doom about AI scenarios, you would be seeing this kind of breaking news in popular culture about technical AI, that AI is helping old lady cross the street, it plays with kids, cooks food, hangs around sans drama. In case you're wondering, how come we never saw this kind of a breaking news item on CNN? It's because I made it up, it's fake news. Basically, it turns out that we typically keep hearing about AI not in the sense of AI agents working with humans. So there's been essentially a sort of a curious ambivalence that AI research has had with humans. Our system seems to be happiest either far away from humans, like either spirit or opportunity or curiosity, are basically in some adversarial stance with humans, essentially creaming the heck out of us in various kinds of board games. It's almost as if we wanted to help humanity. It's the people that we AI researchers just can't stand, paraphrasing something that John Lennon said, right? So I was this is something that has been weighing on me for several years, and I've seen sort of my research program for the last several years has been in terms of the challenges of human-aware AI systems. How do you get human AI systems to collaborate with us as companions? So I gave like a talk 3 years back at a AAAI that sort of stood up as an AI magazine article on the challenges of human-aware AI, and most recently, in that Hill thing that Mike mentioned, I wrote a column sort of giving the current state of the area in AI for lay public. What I want to do in today's talk is sort of give you some of the technical background, in as much as my group has been working on making some of these challenges come to fruition. So I was sort of asking in my AAAI talk back in 2018, why isn't human-aware AI all over the place already, given that pretty much everybody who thinks about AI thinks of AI agents as working with humans, at least outside of AI, and why we should be pursuing it, and of course, some of the challenges. And one of the points I kind of made there, and that's what sort of repeating here, is having for AI research to take humans into account. So we have our AI agents work with humans in the loop. It's not sort of a dilution of our goals. It's really a sort of an expansion of our goals, of the scope and reach of the AI enterprise. After all, it's been said that we had developed evolutionarily these crazy large brains we have, not to run away from the lions of the savannah or the tigers of Royal Bengal, but to really strategize, deal with each other. So this social interaction is what really apparently led to some of the brain size increase, at least speculatively from evolutionary theories. If you don't believe that, of course, we do know that we are always modeling each other's mental states and what are the other people thinking about me and what should I do to counteract that. Here is a great piece from Friends, the show that some of you may have watched, where Phoebe is saying they don't know that we know that they know that we know. So you can actually play with these mental models both to cooperate and to strategize against, in adversarial stances. Obviously, human-aware AI systems are needed in many places. From the very beginning, actually, people did realize that things like intelligent tutoring systems and social robotics, the researchers in those areas have certainly taken humans into consideration in designing their systems, because that's the whole point of those systems. But then that's not the only pieces where you want your AI systems to work with humans. Pretty much even quotidian interactions between AI systems and humans, for example, assistants, human-aware digital personal assistants, or office or hospital assistants, and also in teaming, some of that is possible now, some probably more so in the near future, elbow-to-elbow teaming, remote cognitive teaming, such as in search and rescue scenarios, and even factory robots, which can actually explain their operation to new humans in the loop. Okay, so in some sense, increasingly, if in fact you believe the hype that AI is everything, and AI actually eats computer science, then human-computer interaction really will become human-AI interaction. And so we really should understand some of the challenges there and how to solve those. Within United States that I'm pretty familiar with, the US national priorities for AI include 10 areas, and number 2 is human-AI interaction. And then there's several research programs for example, DARPA has ASSIST, ADAPT, and a more recent one, PGT, and so on, many other programs looking at these kinds of challenges. So getting to this talk, what do I want to say? What I really want to get across is, what does it take for an AI agent to show interpretable behavior in the presence of human agents? And The simple answer, it turns out, is managing mental models. Some of you will say, duh, obviously that's kind of obvious, but some of you may not have thought about this. This is something that psychologists have always been talking about. Something like Salient test that some of you may be familiar with points out that kids recognize that what they believe about the world is different from what others believe about the world, and this is when they realize that they actually can lie. Not only they can cooperate by actually making clear what they believe in, but also lie. And I joke around that I was extremely happy when my son started telling his first lies like 25 years back, because I knew he had a working brain which essentially is able to model other people's mental states and realize that what he believes in is different from what others believe in. So managing mental models becomes the important aspect. So that gets me to the overview of the talk, which is sort of a perspective on how to do this from a bunch of research that we have been doing in the past 6 or 7 years. So the overview of the talk is I basically want to get you to see that effective human-AI interaction requires AI systems to be able to manage human mental models. These include not only the human's model of their task, but also human's model of the AI agents or the robot. So this is at least a second level. In general, mental models can have infinite regress, and psychologists have basically talked about the fact that humans tend to use about 3-level nesting, and I will specifically focus today on the second level of nesting because that winds up leading to explicable behavior as well as explanations. We'll get to that in a minute. And then managing mental models brings up both inference and learning challenges. I'll talk about how we deal with them, and then frameworks for human AI interaction, because we are a bunch of computer scientists and we might think, well, we are humans, we know what humans want. And so here is a solution that is not going to be up to snuff because essentially, you really need to have a systematic ways of evaluating whether your theories of assistance and so on are actually acceptable to the humans through systematic human subject studies. And then finally, I'll end it with by pointing out that mental modeling capabilities allow AI agents not only to cooperate just like they allow kids, not only to cooperate with the humans, but also to manipulate the humans in the loop. In fact, people are worried about deep fakes. Eventually, we have to start worrying about head fakes, which is your AI agent making you believe something that's not actually true and using that to an advantage that's kind of not beneficial to you. As again, I'm not saying that you're going to be out there trying to design an AI agent that way, but they can be hijacked by somebody else. So in fact, I would argue that huge amounts of problems with Facebook and other social media are caused by the fact that people didn't quite realize that they are talking to something like an agent that is actually profiling them. When we talk to other humans, we're already on guard. People who are pouring their hearts out to this Facebook, giving away lots of information, and then of course it got misused in multiple ways, as we found out. So it introduces several new ethical challenges that we need to be worried about. Before I go into details, let me show the people who actually do most of the work that I'm talking about, which is my group of students right here. And so most of the work that I'm talking about is done by one or the others of them. In particular, Anagha, who just graduated this, defended a thesis this week, and Sharath and Tathagata, who got an AI Tend to Watch award this year. He graduated a couple of years back. They've actually done a lot of this work that I'll be discussing. Other people also have been involved. Okay, so let me start with how we handle this sort of human AI interaction. And it starts with, as I said, it's about mental models. So let's start with a tale of 3 models. Okay, when I say, for the rest of the talk, when I talk about models, I just want you to understand that I'm not wedded to the specific language, although a lot of our work was done with relational representations in PDDL or planning domain description language. We've also done work with other kinds of models, such as the dynamic programming models that have been used in MDP and RL communities. And these are all connected anyway. The important thing is what's the content of these models. You can think of the contents of these models essentially as including initial state of the world, the goal state, the actions, the observation capabilities, as well as the current plan, if any, of either of the agents. And we have two agents that we're talking about, the robot and the human. I'll say robot, but I don't particularly care about embodied AI systems alone. I will actually show you that we work also with basically software AI systems, software artifacts which are supporting us, may not be embedded. So I'll just use the word robot in a more general sense. Okay, so that's what you have to keep in mind when we're talking about models. This can be represented obviously in PDL, but they can also be represented in your favorite languages. So let's start talking about like the simplest single agent, which is living in the world. When the agent is actually just by itself, it really has some approximate model, an executable model of the world. What it hopes is the executable model of the world, MR, we'll call that. And it can use that to make its own courses of action and live in that world. So it, basically given its reward metrics, given its goals, it can actually come up with courses of action that are consistent according to it, MR, and then hope that they can be executed in the world and start executing them. So this is something that we know in AI 101. Okay, the moment you put a human in the loop, which is another agent, but it's not another artificial agent, this is human agent with all the human foibles. So one of the first things that would happen is that the human winds up having a model, M of H, for the task. That means they have their own goals, their intentions, and their observational constraints, and so on. And so the robot, to be able to at least sort of at least not get away, not get into their way, or hopefully try to help them, it needs to have some idea of this MH, and I'll call that MHR. So this MHR is robots or the AI agents' approximation of the human's model. That's the first of the mental models we are talking about. And you would have heard about this in many places when you talk about basically robots or AI agents anticipating human behavior. This is what we mean. We are anticipating human behavior by using MHR. This can lead to assistance, at least getting out of the way, so avoiding the human so that you don't get into their way, and sometimes also to support teaming, etc. So this has been actually done quite a bit in the community. In fact, I was looking at the Strachey lectures, and I know that I think a couple of years back, Sarit Kraus gave a talk, and she was mostly a lot more interested in just sort of the human behavior learning. So that is kind of, you can think of it in terms of MHR. We have done some of the work in those directions too. For example, you can do intention recognition of the human model, basically with, in this particular case, an emotive brain-computer interface. This is nowhere near as fancy as the neural link that Elon Musk is trying, but even a simple thing which can wordlessly, without actual explicit communication, the robot is actually able to see in this the one in the lower window that Sachin, who is the subject there, actually wanted to reserve one of the blocks, and it realized that, and it was actually using only the other blocks. So things of this kind. So basically intention recognition and anticipating what people want and avoiding getting out of the way can be done. We have looked at that. In the same direction, actually, robots can project their intentions into the humans, either by actually speaking, but in this particular case, we are using augmented reality, HoloLens, which sort of provides to the human not only what they're seeing, but also additional information that the robot is projecting about its goals by pointing out to particular blocks and so on there. Okay, so these are things that are possible. But I'm not actually going to be talking as much about that part. The one that I want to talk more about is essentially the fact that the moment humans are interacting with an AI system, they will wind up making their own model of that AI system. So if they see a robot, they will essentially have some model of the robot, MRH, which is the task model that they attribute to the robot. Some of these can be very magical. Some of them, if the experts in the loop, they might have some really good sense of what the robot's goals are, what it's actually capable of. So there is MRH, which is the humans model. And the AI agent, the robot, essentially now needs to have an approximation of that too. This is the second mental model that I will spend most of my time in the talk talking about how to exploit and leverage that. So the MRH here allows the agent to anticipate human expectations in order to either conform to those expectations, or if it cannot conform, then explain its own behavior in terms by sort of modifying MRH. So tell the human, you have to change your expectations on me in the following ways so that my behavior makes sense to you. So to me, explanation really is this dialogue that the AI agent has with the human, changing their MRH, which is their model of the agent. Okay, I will mention that MHR and MRH are different from MH and MR. MH and MR are for the human and for the robot sort of execution models. These are models that they're hoping are executable in the world. The actions should have real preconditions, and hopefully, in fact, the preconditions are satisfied. There should be high probability that the action actually works. Unlike those, MHR and MRH are expectations. They're really expectations on models. We will mostly, for this part of for this talk, we'll talk about like the maximum likelihood expectations maybe, but in fact, they can even be like a distribution over the models. And they don't have to have any execution semantics at all. They're just being used by the agent to make sense of the other agent's behavior. So it's worth keeping that in mind. So given those, it's basically the way the longitudinal human AI interaction cycle works is we'll assume, and I'm mostly focusing in this particular case in terms of the MRH, which is the humans model of the robot's task model. And so you start with an initial estimate of MRH, that is, the robot starts with the initial estimate of MRH. And I should mention here that from my perspective, from an AI researcher's perspective, if an AI agent is working with the human, the only controllable variable really is the AI agent. The most obviously controllable variable is the AI agent, because you can't, you can possibly tell the human, please do this, but they don't necessarily have to actually take your advice. So in essence, much of what I will be discussing is from the perspective of the robot. So not only does it needs to anticipate what the humans are thinking of its capabilities, it also needs to and understand what the humans think of its capabilities, and use that. That is MRH. And we'll assume that we start with an initial estimate of MRH. And I'll talk to you, in some cases, they start with a shared model initially. Other cases, you can actually learn from existing behavior traces. I'll get to that part a little later in the talk. And then you sort of have this loop. There are two pieces in the loop. One is the model following, where if the AI agent thinks that there is a sort of an understanding between what the human thinks its model is, then it can just conform to it, MRH. And conforming to it is really explicability, and I'll talk about it now a bit in a minute. So an AI agent basically making its behavior such that it is in accordance with what the human agent expects it to do, that is explicability. There is another notion, there are other notions related to model following, which such as predictability, which is sort of locally the behavior should be consistent with what the human expects. Then there is the model communication, sometimes actually conforming to the human model winds up being extremely costly. And so in those cases, essentially, the robot basically decides to do what is optimal for it. I'll give you an example of this in a minute. And then it realizes upfront that since this behavior is different from what the human would be expecting given their model of its behavior, it needs to change their model. And so that's what the explicability, the explanation part starts. Explanation really is communicating changes to MRH, either as a heads up upfront or as a post facto explanation after the behavior is done. There are other ideas such as legibility, which is sort of explanation except typically with implicit actions, and design, which is sort of changing the environment in such a way that the environment itself gives a heads up to the human as to what your MRH is. I'll also touch on a little bit on the design part too. So that's basically the longitudinal human-AI interaction cycle. And I'll sort of flash this slide a couple of times in the next few slides. So let's talk about model following part. So as I mentioned, we actually use two kinds of use cases. One is on the left-hand side, where basically you have embodied robots. And in this particular case, embodied robot, the fetch robot is going around in a mock search and rescue scenario with the human commander safely ensconced in some other place and having like a camera dialogue with the robot. On the other side, on the right-hand side, we are looking at a planning decision support system. If you have a mission planner, NASA mission planner or somebody, they are trying to make the plans themselves, and the decision support system provides suggestions about how to complete their plans. So these two are the two general kinds of scenarios that we look at. The challenges, they look very different syntactically, but the challenges about how an AI agent interacts with a human wind up being quite similar in both cases. And as I'll show you as we go forward. Okay, those are the use cases. So, and then, given that, I'll also show mostly the robot use cases in the demos because those are more fun to watch. So in the case of model differences with the human in the loop, that means the MRH that the human has is different from MR, that the robot's actual model. So what that means is the plans that are optimal to the robot according to its model MR might actually not be optimal according to the human's expectations of a robot model, so MRH. So what the plan that is optimal in MR may not be optimal in MRH. That's all I'm saying. And when that happens, there is a surprise on the human's part because they're basically seeing a behavior by the robot that they didn't expect. So this leads to inexplicability or inexplicable behavior. At that point, the robot has two options. It can conform in the model following case, or change the model that the humans have, that is MRH, which is the explanation part. And I'll talk about both of them in a context of this search and rescue scenario. So imagine you have in this scenario, you have the human and the AI agent, the robot, essentially start with the correct map of the environment. In this particular case, this is the 5th floor right outside my door and in computer science department right here in ASU. And presumably there is sort of so the model of the map of the environment is known upfront, but it turns out that there is possibly some sort of a disaster, and so there possibly are rubble. There may be paths that are closed, maybe actually be paths that are opening up, which means that the internal agent, the robot, which is on the floor, might actually wind up realizing that the map has changed, but the human still thinks that the map is the same as before. And so essentially there's already a difference between MRH and MR, and then that needs to be reconciled through the through this interaction process, either by the robot being conforming to what the human expects or by changing the model. So in the context of conforming to the human model, in this particular case, in this picture, what's happening is a particular path that would have been the shortest path is closed because there is an obstacle. Think of it as some huge rubble there. So if you don't want the human to be surprised at your behavior because they're actually expecting perhaps that you will be coming out of this particular corridor, then you have to conform to the human's model. So in this particular case, it wound up removing the rubble. So it's costlier than just taking the next best path. That's what is explicable behavior. So to be able to provide explicability, given a goal, the objective normally would have been to just find a plan that is optimal with respect to its own model, but now it needs to find a plan that's not only optimal with respect to its model, but it's close to what is expected by the human based on their model, which is their MRH. And so it becomes a sort of a multi-model planning problem. And then this can be done, I'll talk about, this becomes sort of a more complex optimization problem, to actually come up with this kind of an explicable plan. And what we're trying to do is sort of reduce the distance as much as possible. Sometimes making the distance zero actually might be impossible because humans might be expecting magical properties that the robot doesn't have, such as completely removing the rubble from a particular corridor. Okay, so now, conforming to the explanations is costly. As I said, you actually have to remove rubble or something in this particular example. So then you might want to communicate changes to MRH to the human, and that would be the explanation part. In this case, if you could hear it, it was basically yelling at the top of the voice that the particular path is actually blocked, and because of which this other path is being taken. So in essence, it's just changed the model just partially, a delta change to the model that the human, and if the human actually pays attention and takes that into account, then all of a sudden the robot's behavior is as explicable, with respect to the changed model. So the explanations really has been talked about a lot in explainable AI systems, and explanations have been talked about a lot. But when human and AI agents are interacting, it's best to think of explanations essentially as this reconciliation of models. This is sort of close to psychological validity too, as I'll talk about it later. But in essence, what we are saying is that an explanation epsilon given a plan pi that the robot has essentially decided to act on is such that if you add this epsilon to current MRH of the human, then this plan pi will be actually optimal in this changed model. And it's also already optimal with respect to the robot's model. That's why the robot dictate. Again, I'm using the word optimal. It's easier to think in terms of essentially optimality from a theoretical analysis point of view, but in practice, essentially, you're more or less trying to say, I'm doing this and you're expecting a different plan, and this is the changes that I need to make to your model such that my plan would be in the top K plans that you would see me doing. Okay, but optimality allows for a much better theoretical analysis. Okay, so that's the explanations as model reconciliation. It turns out that, in fact, computing these explanations winds up being a meta search in the space of the models themselves. I actually skipped a little bit about the representations of the models. We use, in much of this work, we wound up using planning domain description languages, which have actions and with the preconditions and effects in symbolic terms. And so if you have a model with a bunch of actions and their preconditions and effects, another model that the human has with a, either similar or different actions with their preconditions, what the robot is trying to do is essentially modify the human's model MRH that they are attributing to the robot. This will involve, for example, changing the preconditions, changing the effects, or changing the costs of the actions that the humans have attributed to the robot. And this search essentially has all sorts of interesting properties. Using this model space search, you can come up with different kinds of explanations, both minimal explanations that will just make the human understand why this behavior is fine in this case, but might question this explanation a little later because you do something that's inconsistent with this explanation. Or you can also come up with monotonic explanations, which will essentially not cause that confusion. Monotonic explanations will be costlier to compute. And in one of the cases, you are searching from the human model in the model space towards the robot's model. In the other case, you're searching from the other side. The technical details of this search are actually in this Ichkai 2017 paper that would be, you might want to look at. Even though I sort of mentioned explicability and explanation as if one is the model following and one is the model communication, you can actually combine both of them from a planning perspective, from a reasoning agent's perspective, into a single planning framework. We've we have a paper at IIII this last year, just before everything closed in IIII 20. There's a paper on expectation-aware planning, which essentially considers both ontic actions, the kinds of actions that change the environment mostly. Those are primary effects are changing the environment, are epistemic actions, which are mostly their effects is to change the mental models. That means the communicative actions. And sometimes you have actions, ontic actions can have epistemic effects. That's how you wind up doing implicit communication just by doing actions that have physical effects in the environment, but they also are providing mental effects, mental model changes to the human, right? So the robot has both the standard ontic actions and the explanatory actions. It can model the effects of its actions on both its states as well as the human's mental state. It sort of becomes, so those of you, and especially people like Mike, this is essentially epistemic planning, epistemic reasoning. So here planning becomes a multi-model, and the AI agent uses both its model and the human's expectation model to generate a course of action that contains both explanatory and ontic actions. And so the explanatory actions are such that those are making changes to the MRH that the human has. And after those changes are made, then the rest of the ontic actions, that the plan that the robot is actually exhibiting, the behavior it is exhibiting, would be optimal in this changed model. So you're doing both in the same environment. And the difference between explicability and explanation just becomes whether the explanatory messages part, the E-psi part, is empty, in which case it's just explicable planning. And if it's not empty, then you are asking the human to change their mental model first before understanding your behavior. So that becomes explanation part. It turns out actually epistemic planning has been studied before too. One of the nice things is for just the two level nesting that we are considering, there are efficient compilations to single agent planning. And so that's the trick that we use to make this doable, tractable. So the details of how the compilation works are in this IIII 2020 paper. Although I looked at the robot changes, basically the embodied robot scenarios, as I said, the same kinds of explanations can be used in the decision systems. So this is a radar system that we use to kind of provide decision planning support to humans in the loop. We had some work with NASA as well as some ongoing work in ONR, Office of Naval Research. In both cases, people are interested in making plans and people want to be in charge, and the system should be helping them. The AI system should be helping them. And the explanations, when you provide a suggestion, why did you provide this suggestion? If the human were to ask, you should be able to provide an explanation. And that is something that our systems are able to do using these kinds of theories. Okay, so coming back to the longitudinal human AI interaction cycle, now what I want to do is, having talked about explicability and explanation, I want to talk about the learning part. So basically, where did the original MRH model come? Sometimes it is, as I said, it may be there as a shared model initially. Sometimes it has to be learned. So in some cases, such as the USAR scenario, human and AI agent will both start with the same shared model. So all that is needed is tracking the model drift. Even if the robot doesn't know the model MRH with certainty, it can reason with multiple possible models. If you are not sure which is the specific model the robot in the human has, if you don't know MRH specifically, but you think that it's one of these K models, or if in the most general case you have some Bayesian distribution over these models, especially the case where you have K different models, we can actually reason with these K different models and provide conformant explanations or conditional explanations with respect to these models, sets of models. There's a paper back in 2018 on that. In other cases, in the end, you actually have to learn these models from scratch, some behavior traces, if it's not being provided by upfront by knowledge engineering aspects. So in that sense, AI agent would need to learn the human mental models from the traces. One thing that we do want to keep in mind is, unlike MHR, which is anticipating humans, which can be learned from human behavior traces that have been cached over large amounts of time. You've just seen too many humans working on that problem over a long period of time, and you just use that. MRH which is requiring basically that is humans take on what the robot is doing. And so that doesn't just come from the human behavior traces. Oftentimes, we have different expectations of the AI agent than what we are capable of doing. So for example, if you walk into a room and you see a robot that starts dancing, you would be surprised because you don't expect robots to be able to dance, except maybe in a couple of videos that you may have seen. So whereas humans, you do expect them to be able to dance. So the MRH really requires traces that human likes over the traces of the robot's behavior. So that's a slightly harder learning problem. And sometimes you may actually have to deal with vocabulary differences too, and I'll talk about that in a minute. With respect to one of the points that I want to mention here is that, as I mentioned, MHR and MRH are both expectations on models. And so they really don't have to be in any specific format such as PDDL format, that MR and MHR for our robots, because they actually have to plan with them. But the MHR and MRH are only sort of expectations, and they can be represented in many more flexible ways. One of the things we did essentially is to learn human preferences of the robot behavior as labeling functions during a training phase. And use these labeling functions internally. The robot then learns this labeling function. There's a paper in 2017 which sort of learns this as a sort of a CRF and uses this labeling function as part of its behavior, its planning process. So it computes this distance between the plan it is making and the plan the human expects in terms of this labeling procedure that it learned. And so that is a way you can be explicable. It turns out that the same idea for learning, so you're essentially in this particular case, you're learning MRH not by learning it in explicit actions, preconditions, effects type, but in terms of just a labeling procedure. You could do the same thing even when you're not doing explicability, but you're also providing explanations. In that case, all you need to do is improve the training scenario, expand the training scenario such that you are showing a behavior as well as some explanatory messages next to them and asking humans to say whether or not the behavior makes sense, which parts of the behavior is making sense, which doesn't. And this is the training phase. And having used this, then you can then have a labeling procedure, which can then be used to compute the explanations on demand without having an explicit MRH, which is in terms of actions, preconditions, and effects. So this is why it's important to understand that MRH and MHR are just expectations. They don't have to be executable models. Having said all of this about explanation, some of you probably have heard a lot about explainability and explainable AI in the context of machine learning systems. And I want to kind of make a connection between all I discussed and some of the body of the work there. They're both similarities and differences, and it's worth understanding. XAI is hard, but mostly as a debugging tool for inscrutable representations. So for example, oftentimes you'll wind up, the system basically says this particular dog is an Alaskan Husky, and you ask, why do you think it is an Alaskan Husky? And the system points out that the snow part of the pixels, the saliency region is the snow pixels. And then you might say, aha, you don't really understand Alaskan Husky at all. You're just understanding snow and the correlation of snow being present next to the dog. But notice, first of all, that this is a debugging explanation, and it's a pointing explanation. And really, you can't actually point to many things. Oftentimes the kinds of behavior I'm talking about, which is a sequential behavior, as to why did you do this decision, if you want to point out, do a pointing explanation there, you need to point to a space-time tube, which is extremely hard and very unwieldy, which is why civilization progressed by us sort of developing these symbolic vocabularies through which we provide explanations. And that's the kind of model-based explanations that I've been talking about till now. In fact, if you have looked at this adversarial example scenario that many people have probably seen about that school bus on the left-hand side after a little bit of noise becomes ostrich on the right-hand side, even though you don't see it as an ostrich. A classification system might very well say with high confidence that it is an ostrich. And if you ask it, tell me which part of this makes it an ostrich. Point to me what parts makes it an ostrich. That would be a useless explanation because it'll just show a couple of several pixels, all over the picture, which don't have any rhyme or reason from your point of view. But as far as the system is concerned, that made the class for this an ostrich. So the point being that pointing explanations are the primitive explanations that are mostly useful only for debugging. Explanations are critical for collaboration, but they're not really a soliloquy by the agent. It's not just talking to itself. It's trying to make sense to the human agent in the loop. And that would require a lot more than pointing pixels. And the model reconciliation view that I've been talking about here views closer to psychological theories of explanation, such as the ones that Tony Alambrazzo and co talked about. That's a useful thing to keep in mind. So one other thing I want to mention when I'm talking about here is that handling differing vocabularies is another important issue that will wind up happening. We did not talk about whether the models are on completely different vocabularies, MR and MRH. When you have an inscrutable system, which essentially basically is learning its own representations, and so there is no direct connection to any concepts that the human understands, this is where you are hoping that you'll be able to just point to the pixels or something that is common between us and point to that particular substrate. But really, if you have things like sequential decision problems, you will need to provide the explanation in terms of concepts that the humans can understand. And so ongoing work that we have in our lab, as well as some other work that some other people like Dean Kim have done, involves essentially translating the explanation that you have into the vocabulary that the humans understand. And to do that translation, you need to first learn the translation. So you understand mappings from symbol to pixels in this particular case, and then convert the explanation into these symbols. And when you do that, it will be possibly an approximate explanation, but that's way better than just sort of throwing a big trace of your reasoning to the humans and say, this is the reason I did it. Actually, I should mention that the trivialist form of explanations are those where you say, you will understand what I did if you take my brain. Here, take it. And that is one of the trivial forms, and we assume that that's not a good explanation at all. That's why we actually search for smaller pieces of changes to the MRH. That will be enough for the human to understand your decisions. Just to put this in like a classification kind of a scenario, we have some recent work which shows that sort of thinking about mental models, even if it's not sequential decision-making problems, can be quite useful. So for example, in many classification systems are typically evaluated only in terms of their accuracy, how often are they correct. But I would argue that really it's equally important to see when they are wrong, how badly off are they. So a system which makes an egregious misclassification, humans will lose trust in it. By the way, the word trust is the first time I'm mentioning it in the talk, but the interaction between an AI agent and a human, humans might kind of might engender trust in humans if in fact they can make sense of the decisions that the agent is making. So in these particular pictures that we are showing, we essentially have developed this system where it not only takes into account classification accuracy, but misclassification egregiousness, and using that, our system, for example, will be able to come up with better kinds of misclassifications, even if it is asked to misclassify, than the existing system. So for example, some of the examples there are showing that if you have something like a tabby on the very first top left corner, the existing systems might just, when they make a mistake with this, they might just say it's a remote control. And our system will say it's a tiger cat. So because in essence, it's also looking for cost of the misclassification. And that's something that you can do with respect to mental models. So there's a bunch of things that can be extended from this. For example, communicating the model may or may not guarantee interpretability unless the human has the inferential capacity to compute the optimal behavior from the model. I sort of pushed it under the rug earlier. It turns out that you can use foil-based interactions, which is a bunch of work that we have done there, where the humans just ask, why not this other behavior? And you only provide reason as to why that other behavior is not as good as the behavior you have shown. And this will be easier sort of to understand than just deltas to the model with respect to which you need to be able to see that the behavior is actually optimal. And similarly, when you provide information to the humans, the real question is also whether the agent is actually, humans are paying attention to the communication, and that involves two parts. Is the communication actually perceivable, at least in theory, at least? So for example, if I was giving this talk on a radio without video, if I started showing you slides, holding them in my hands, the joke is on me because I'm not reasoning about the fact that you won't be able to see what I am showing you. So that is basically reasoning with the communication perception modalities. The other is, even if you see it, you may not pay attention to it. That is attention management. That is something we haven't done much, but in fact, it's been done by others such as Eric Horvitz, in the context of the old Clippy, the Microsoft assistant, which is basically figuring out what is the best time to tell humans anything so that they're likely to pay attention to it. So in terms of the foil-based explanations, for example, we can, here's a bunch of papers that we have where the humans basically ask, why not this behavior? And that is, they'll provide a plan, a partial plan or a complete plan, and say, why aren't you doing this one against the one you are currently doing? And you can use that question itself to figure out what level of abstraction in the abstraction hierarchy of models the humans are in, and use that knowledge to provide the right kind of explanations to them. That's like the file-based explanation. We actually did this in the context of this radar system that we were talking about, where we provide a longitudinal dialogue between the agent and the humans. When the human actually provides a file, not only can we provide an explanation as to why that file won't work, but we also realize that that question means that the humans really would like the plan to be closer to the file. So then we do a replanning scenario where we will wind up coming up with a plan that's closer to the file, even if it's a little less optimal. And there's a demo at IIII that talks about this. We also extended these models to also consider multiple humans in the loop. So essentially providing customized explanations to different humans at different times, based on their mental models. And then I talked about this controllability of controlled observability planning problem. This is something that Anaga has done, where essentially the system can reason about what can and cannot be seen by the human, and use that both to make sure that they see that the help is being given, and also, if it so pleases, obfuscate to people in the loop who it doesn't want them to understand that this help, it can obfuscate that too. So that's also possible. That's a IIII 19 paper. And then, more recently, Anaga has been looking at this proactive assistance part, where essentially you are reasoning about the fact that help should not only be given, but should be seen to be given. So at least you should be able to reason about the partial observability aspects of the model observability aspects, and make sure that the human understands that you have provided the help, either by explicit communication, or in Anaga's work, it's actually by implicit communication. So you wind up showing that you are transporting certain objects, and that will sort of provide communicate certain messages to the humans in the loop. So I just want to quickly go over this, and maybe in a couple of minutes. I know that we're very close to end. So the framework for human interaction really cannot just be made and said, they work because we are humans and we think it works for us. So our solution for this has been interdisciplinary collaboration with the human factors researchers. Nancy Cook, shown there, is a colleague here, and she was a past president of the Human Factors Society. And so we work with her and her group in setting up systematic human subject studies to actually check whether the kinds of explicable behavior as well as explanations that we are coming up with make sense to real live humans in the loop. And doing human subject studies is pretty painful. But I would also say that anybody who says they are into human AI interaction but haven't heard of the word IRB, which is Institutional Review Board certification, are probably making it all up, because without that you have no clue as to whether or not these things are actually working. So in fact, there's papers in both HRI and HCI journal that show how the kind of explanations that we come up with are seen to be useful in collaborative behavior with humans. Okay, the very last thing, mental model capabilities allow agents to manipulate the humans in the loop. As I mentioned, they can allow for head fakes. This sort of leads to a bunch of ethical quandaries for any work which starts thinking, allowing AI agents to mental model humans. Evolutionarily, mental modeling allowed us to both cooperate as well as compete or sabotage each other. But really, you can't just stop agents from having that ability, because without the mental modeling, they won't cooperate with you even. So you will have to essentially deal with the Pandora's box that has to be opened. HAI systems with mental modeling capabilities bring ethical boundaries, additional ethical quandaries beyond the usual, oh my God, autonomous robots are going to kill us all, such as, for example, automated negotiating agents that misrepresent their intentions to gain material advantage. Your personal assistant that tells you white lies to get you to eat healthy. As I already mentioned, people would have been actually more guarded with social media if they realized that those platforms are actually actively profiling them. We are already on more of our guard when we're dealing with other humans, but sometimes we don't realize that a Facebook is actually an AI agent which just doesn't look like a human, but it has some of the same capabilities in terms of profiling. So, in particular, with the social intelligence scenarios, humans' example closure tendencies are far more pronounced. And so we need to be very careful about how to deploy these technologies. As I said, head fakes really are a lot more powerful than deep fakes, and we do need to worry about them. But then again, every tool is actually a weapon too, if you just hold it right. And that's true also for these kinds of things. In our own work, we actually have shown that model reconciliation can be used to tell lies of omission as well as lies of commission. And then this work by Anaga that I mentioned earlier actually shows, for example, that in this particular case, in one case, the robot is making sure that the Anaga sees what it is doing, what the robot is doing. In the other case, it actually distracts her to do something else. And so basically, it's manipulating the perception model for Anaga. And so this is like signaling friends and head faking enemies simultaneously. These are things that can be done. The papers on this in 2019 AAAI and AMAS 2020. Finally, we did, when I mentioned that lying robots, we did do a study saying when can AI bots lie? We studied under what conditions people are willing to be told white lies, and there's a paper on that in AIES system conference. So I'll stop here. In summary, basically what I was trying to get to you is that effective human-AI interaction requires human AI systems to be able to manage human mental models, both the model of the human's model of their task as well as the human's model of the robot at the least. You could do crazier things with infinite regress, but in fact, you can do a lot of useful things with just the second level models. That's what I've tried to tell you. Managing mental models brings up inference as well as learning challenges. And these frameworks for human AI interaction have to be evaluated with actual human subject studies. And then mental modeling capabilities do open up new ethical problems, and we have to be careful about them. There's a paper in AI magazine which sort of gives an overview of some of these issues, and then we also just wrote sort of a draft of a book that's under review, on explainable human AI interaction planning perspective. With that, I'm going to stop and thank you for your attention.
Thank you so much for that, Rao. That was fantastic. So we are ready for questions. So please enter some questions in the Q&A. There is, if you look on your Teams, there is a button on the top right for with Q&A. There is a little question mark, a speech bubble with a question mark on. If you click on that, that will get you to the questions and answers. Let me kick things off. So I absolutely see where you're coming from and where you want to go with this, but how far can you get with this towards to kind of human level modeling? How far will this take you? Is there something that's missing, or do you think this is all that we're going to need?
Meaning what? Human level modeling in the sense the way we deal with each other?
Yeah. Yeah.
I mean, this is partial steps towards it, and it's very useful in actual quotidian interactions between human and AI systems. I do realize that we do allow for sort of larger amount of nesting when we reason with each other. Oftentimes, in fact, one of the interesting things which I didn't talk about is you can engender trust in somebody by doing what they expect you to do. And once they start trusting you, you can actually use it to your advantage. So in fact, we have a paper where we sort of reason about how much trust the robot should engender so that it's not required to be explicable, in the sense you're not being monitored as closely. So that it turns out that given that people understand this already, when you and I interact, if you always do things that I expect you to do, I start wondering, instead of not being surprised. In the beginning, I'm not surprised because you're doing what I'm expecting you to do. But if you're always doing what I'm expecting you to do, then I'll wonder that you have other ulterior goals. And then so that will basically bring in additional nesting of the mental models, which we don't deal with right now. I would certainly think that is something that will be important in bringing it closer. The other thing, of course, is really how we wound up, human-human communication, we wound up developing this sort of a common shared vocabulary, over a period of the evolution as well as our going up. And this is something that is very important for AI agents, in particular those which are learning their own representations in particular, because the representations they learn may not have any connections to what humans understand. And so this idea of translation, this is something that's going to be quite important. So I don't really know. This is still a big issue as to whether my thinking is in the same words that I'm talking to you, or I'm thinking in a different way and I'm talking to you in words that you will understand. And this is something that AI agents have to deal with a lot more. And this translation problem is something that I mentioned some of it earlier, but that's going to be another big issue in getting,
Okay, so we have a question that's come in. It's from Max Van Cleek. Max says, thank you for a brilliant lecture. How is this approach similar to the ways that intelligent tutoring systems model learners' skills and understandings, and then cater lessons and follow-on skills reinforcement appropriately? Are there existing similarities, and do you think your approach will enable intelligent tutoring systems to be better tutors?
Yeah, that's very much online. So in fact, I should have mentioned that when I said human AI interaction, I didn't quite explain who is helping whom and who is trying to get out of whose way. In the way we do the work, actually, the robot could be the teacher, the robot could be the student, the robot could be peer-to-peer, and the ITS basically is the robot as the tutor to the human. And many of these issues actually, in fact, as I mentioned in the very beginning on the human-aware AI application slide, people who have always given respect to humans in the loop are intelligent tutoring systems people who, like Kurt Van Len, my colleague in the third floor here, and other ITS people. They've always, essentially, they didn't have the luxury of saying, let's ignore humans. They basically, the whole point is trying to teach the humans. And so, yes, there's a very significant connection between the ITS literature and the work that we are doing. We actually have papers on applying some of this model reconciliation framework in teaching scenarios that, there's an ICAPS workshop paper that's available from my homepage. In fact, one of my students, current student, Sachin, who was actually in one of the earlier videos where he tries to get away from the robot hand, he worked with Kurt and he's working with me. And so there is this obvious connection that ITS systems and human AI interaction are very much connected. One typical issue has been that ITS systems tended to be sort of more semi-automated oftentimes, and the level of explanations that they provide are somewhat different from the kinds of explanations we tended to provide in the work, but they're very much complementary, and they would be lessons that we try to learn from the ITS literature and also port back. Yeah, I think certainly that's a clear-cut case. In fact, DARPA has this new project coming up called perception guided task training or something, where the robot will teach humans how to do factory workers. An AI agent will teach factory workers how to do new physical activities, for example. So it's a robot coach, and that winds up having all these issues. You need to have MRH, you need to also have MHR, and use them to provide these kinds of support.
Okay. Yeah. So everybody out there, please ask your questions. We've got another few minutes while we're waiting to see if there are any other questions. So one other one from me. So I was really pleased to see you allude to the work on the social brain hypothesis, which is this idea that we have big brains, which enables everything because we have large social groups, and we need to keep track of complex social relationships. And the famous work there, I think, is work by Robin Dunbar, the Oxford evolutionary psychologist. Which is lovely work. It's the kind of work that I look at and think, well, I wish I did that kind of research. That's. So when I think about that work, I mean, the example that I use to illustrate it is this 6-word dialogue that's due to Steven Pinker, where Bob says, "I'm leaving you," and Anne says, "Who is she?" Right. And I love it because it's so crisp, 6 words. And again, it's incredibly rich, and we all understand what's going on there. Right. And we can all fill in all the details about what's going on in the relationship between we can draw rich pictures of these two individuals based on just those 6 words. And that a very important part of that understanding is our kind of common sense theory of mind that we all have. So what I'm puzzling over, and this is entirely independently of your talk, is it a target? Should it be a target of AI to build machines that can understand that dialogue? I mean, you imagine there's a robot in the room with Bob and Anne. Should it understand? Should it do this modeling and understand that dialogue?
I think it certainly. I said basically, I mean, so the worry presumably that you have is that it might lead to other unethical uses, or I mean, I think that ship has sailed. My sense is that pretty much everything, I mean, that's what I think. I mean, every technology is dual use technology, and intelligence is the ultimate technology. So everything we do in the context of intelligence is going to be dual use. You cannot stop developing it. You have to develop with complete care taken to make sure that some sorts of ethical framework is being sort of followed in deploying them. So my sense of as an AI problem, as a problem of understanding intelligent interaction, this is a very much relevant to actually fill up these blanks. I mean, using this significant amount of common sense background knowledge, what actually just happened, as to how those sorts of things wind up becoming a problem. Of course, everything I talked about almost can be misused, and so that's just the issue. Yeah, so I would say it certainly is worth doing, and in fact, part of the idea there would be dealing with inferences in the context of rich background knowledge. I've sort of made it simpler by saying the model, only with respect to the model, all the inferences being done, but model plus everything else about the world will come into the picture in doing those inferences.
Okay, so we've got, I think, one last question. So the question is, human working relationships require time to establish. After a few months with a new colleague, one starts to learn whether competence can be relied upon. I think there's a backstory there. And, for example, jargon develops. To what degree are your AIs learning about individuals or different categories of human behavior and building these relationships over time?
Yeah, so that's a fantastic question. So as I mentioned this one slide about longitudinal picture of model following and model communication. This is something that I've sort of used to motivate a lot of our work. Most of our beginnings of our work up until, let's say, last 2 years back was in the first short explanation, but longitudinal explanations wind up being changing your mental model of the human, as well as noticing that their own MRH is changing. A classic example is this idea that if the robot is doing something inexplicable in front of a human the first time, they'll be surprised. The third time, they will still be surprised. By 17th time, they are not surprised. And by the 18th time, when the robot actually realizes that it's making a mistake and starts doing the more explicable thing, the humans are again surprised. Because by this time, they went around changing their model of the human robot, MRH. And this is something that happens in longitudinal scenarios. In that trust work that I mentioned, we are actually trying to use that to see that if you engender enough trust, then you will basically not have to continually show explicable behavior. So if you're shown enough explicable behavior some number of times, the humans basically have higher trust, and so they have less of a monitoring going on you, at which point you can live your life and do more things that are more optimal. Again, when you're doing this, whether in fact that's going to be unsafe or not, that's an actual separate issue. So whether the robot is doing something deliberately unsafe to the human is something that we have to still deal with, but the idea that mental models will be changing during the interaction, and so explanations will be changing as the mental models change, is very much part of the work that we are doing. There are more recent papers. In fact, there's one that I didn't get into, which talks in terms of a Bayesian account of all these things, where you think of what the human essentially has as a Bayesian a prior over the MRH. That is, these are the possible different models the robot has. And then whenever the humans are looking at what the robot is doing, effectively the prior is being updated to be a posterior. And so there are new probability masses over this. And in fact, there's always this possibility that one of the models that the humans have is, oh my God, I have no idea what the robot is doing, which is, we call this M star, which means this is, you admit to yourself that I have no clue what this person is doing. And I just hope that that would be the least likely explanations for the behavior. And the more that becomes the most likely explanation, the more the inexplicable the behavior is. And so updating this distribution over the longitudinal interaction is a great way to answer this gentleman's question as to how do you learn that the robot model is, the MRH is changing over the interaction time frame.
Okay, we do still have like a minute. We have one other question that's come in. Could this kind of modeling be used for machine-to-machine interactions? If so, would you need to change the way you form models of what the other agent expects? And they've written, I'm really sorry if this is a stupid question. We're AI researchers. Our life is spent dealing with stupid questions. So that's fine. So wow.
It's actually a great question. And I thank you for asking this. Yes, it can be done. But no, I won't do it that way, because machine-machine interaction, I would say that the thing that we are missing really, and I hope Elon Musk won't be successful in changing this, is we don't have a USB connector to our brains. So there is no brain-to-brain transfer. Okay, so you can only interact with these humans in this sort of, just like we can't eat pizza over email, we can't learn each other's mindsets by anything other than sort of watching their behavior and making hypotheses. And so that's what makes the human-AI interaction more complex, and human-human interaction also has been more complex because of that. If I was designing robots, in fact, I would say they will have a hive mind. If I have a whole bunch of robots that have to work in the factory, there's no real reason why they have to deal with, am I being explicable to you, etc. You guys all have the same mind. I'll just make sure that you have the same mind. And then maybe somebody from North Korea will have a different hive mind, and we just have to deal with that part. But there are cheaper solutions if it is machine-to-machine interaction. There are some parts of this are relevant, but there's a lot more that is really because of human in the loop here, because I still think that I'm confused. I mean, this is the problem, right? Over the pandemic, we did everything on Zoom except eating pizza, which we had to do physically, and we are sort of inefficient that way. And same thing in terms of understanding each other, we have to do this in this indirect way. And so that makes things harder. But machine and machine, you can still do it in the hard way, but there are also easier ways because you can design the machine world. I'm hoping that we won't design the human world And I'm hoping that neural link doesn't become successful. At least not in my lifetime, because I don't want any of you to have a USB connected to my thing.
I'm with you on that one. Thank you so much for a wonderful lecture. We very much appreciated it. And let me just say again, you are most welcome physically in Oxford when all this is over. We would love to have you. And I think you've now got a whole bunch of people who would love to meet you in person. So you'll be most welcome, Rao. In the meantime, stay safe and thank you again. For those that haven't, I really urge you to look at Rao's pieces in The Hill and also follow him on Twitter if you're interested in AI and for a humorous and informed commentary on the current state of AI. There's no better place to look, I think. So thanks again, Rao, and take care.
Thanks again for the invite, Mike.
Take care.